Hell no, and a massive welcome to all our grade 9 geometry students tuning in from St. Paul American School in Clark, Philippines. I am so excited to be your host for today's explainer. We know your curriculum is rigorously aligned with the Common Core, and today we're going to master some incredibly foundational geometry concepts together. We are focusing strictly on area, composite figures, and similar polygon applications, so get ready to lock in some serious knowledge.
Now, to respect your time and keep your cognitive load perfectly balanced, we have a clear roadmap today. We're hitting lesson objectives, area of composite figures, area of similar polygons, common area misconceptions, a quick formative knowledge check, and finally our geometry lesson recap.
All right, Section 1, Lesson Objectives. Let's take a look right at the finish line. By the end of our time together, you're going to be able to confidently do two very specific things. First off, you'll calculate the area of composite figures. And second, you're going to smoothly apply the area of similar polygons theorem. These are absolutely crucial building blocks for your Common Core math journey.
Moving into Section 2, Area of Composite Figures. Okay, let's dive into this. A composite figure is, at its heart, just a shape composed of basic, simpler shapes all put together. It's like a giant puzzle. So instead of panicking when you see some wild, irregular polygon, you just need a strategy.
To find that area, we follow a highly logical four-step game plan. Step 1, break the whole thing down into simpler shapes, like basic rectangles. Step 2, find the measurements and calculate the areas of those simpler shapes completely independently. Step 3, just add them all up. And step 4, which is so important, always write down your final answer using proper square units.
Let's actually apply those 4 steps right now. Imagine we've got a large, irregular shape. We decompose it into two super manageable rectangles. Let's call them Rectangle A and Rectangle B. Now, Rectangle A has dimensions of 6 meters by 5 meters. Using our standard area formula, length times width, 6 times 5 gives us an area of 30 square meters. Moving on to Rectangle B, that one is 9 meters by 4 meters. Multiply those and we get 36 square meters. Step 3 tells us to just add them up. 30 plus 36 equals 66. And finally, per step 4, our answer is exactly 66 square meters. See? Decomposing the figure makes the math so much easier to handle.
Section 3, Area of Similar Polygons. Let's transition over to our second objective, exploring the fascinating stuff that happens when two shapes share the exact same proportions, but they exist at completely different sizes.
And this brilliantly illustrates the core rule we need to remember. Polygons are similar when their corresponding angles are equal and their corresponding sides are in the same proportion. That proportion? That's what we call the scale factor. But here is the catch, so pay close attention. While the ratio of their perimeters simply matches the scale factor, the ratio of their areas absolutely does not. Because area is a two-dimensional measurement, length and width, you must square the ratio. This is the actual area of similar polygons theorem. If the scale factor of the sides is m over n, the ratio of the areas is m over n squared.
Let's prove this theorem right now by modeling it with some hard data. We've got two similar rectangles. The small one is 10 by 16, giving it an area of 160 square units. The large one is 15 by 24, giving us an area of 360 square units. Okay, so let's find the scale factor of those sides. 10 over 15 easily simplifies to a ratio of 2/3, right? Now look at the areas. 160 over 360 simplifies to 16 over 36, and that simplifies even further to 4 over 9. So ask yourself, what is 2/3 squared? Well, it's exactly 4/9. The ratio of the areas is perfectly the square of the scale factor.
Section 4, Common Area Misconceptions. Now that we've built up that solid foundation, let's check for some pitfalls so you don't fall into predictable traps on your exams.
Now, what's really interesting about this slide is how easily our eyes can totally deceive us. In composite shape problems, you aren't always given every single side length, and a huge mistake is trying to figure out a missing side just by looking at it, kind of guessing. Oh, that looks to be about twice as long as this other one. No way. We can never do that in geometry. You absolutely must calculate the missing side using the given parallel measurements, like subtracting a smaller, known parallel segment from the total known length. Bottom line, never guess, always calculate.
Another major pitfall to watch out for is the units. Let's say you do all the math right. Your area is perfect, but you just forget to write square meters or square centimeters. Well, your answer is incomplete. Also, before you even start calculating the area, you've got to make sure your measurements are in a common unit.
If you've got a length of 4 meters and another of 3 centimeters, you absolutely must convert them both to meters or both to centimeters before you multiply anything. Section 5. Formative Knowledge Check. Let's do a brief low-stakes test of the knowledge we just built together. Get those mental gears turning.
Listen to this question carefully. If the scale factor of two similar rectangles is 2/3, what is the ratio of their areas? I want you to think back to that theorem we just broke down. What happens to a one-dimensional ratio when we move into a two-dimensional space? I'll give you a second to process that.
Did you get 4/9? If so, you nailed it. Remember, you have to square the scale factor. You square the numerator, so 2 times 2 is 4, and you square the denominator, so 3 times 3 is 9. If you got that right, you have successfully grasped the area of similar polygons theorem.
Section 6. Geometry Lesson Recap. Let's bring this explainer to a close with a rapid-fire summary of our focus areas, just to cement everything for your Common Core studies.
So, the crucial point is this. Tackling complex shapes is just about managing smaller, simpler pieces. Decompose those composite figures right into basic rectangles. Calculate any missing sides using the given parallel lengths, completely avoiding guesswork. The sum of your simple areas will flawlessly equal your total composite area. And finally, when dealing with scale, remember that the ratio of similar areas is always the square of the scale factor.
Now, before we go, remember that geometry isn't just stuck in your textbooks. It's literally the architecture of the world around you. Look around the room right now. Seriously, take a look. Maybe it's an L-shaped desk, a uniquely shaped window, or a bookshelf. What complex object can you mentally break down into simple rectangles to find its total area? Keep that mathematical lens active, grade 9. Thanks for joining me on this explainer, and keep up the fantastic work at St. Paul American School.